So, just a quick recap on what we learned in the intro video. Um, you looked at the definition of an acid and a base, and what's strong and weak. You should have got some insights about the real reaction that's taking place, which is this one that I'm hovering over, which is the hydronium ion, which is what acids contribute to, and the hydroxide ion. And both are bad or good depending on what the scenario is, but they're both, if this is in high concentration, this one will be in low concentration, and so there's a bit of yin and yang to them. The only time that you can have them even is at when the solution's neutral at 25 degrees. That's when the pH is 7. But that if the temperature changes, neutral can be a different pH. Because it's endothermic, when you increase temperature, you'll favor the products. So this might go up to 2 times 10 to the negative 7, 2 times 10 to the negative 7. It's still neutral, but the pH of neutral water for a higher temperature than 25 will actually be a lower pH. That's because when the concentration of the hydronium goes up, pH goes down. It's a negative log scale. So you might have something like 6.8 for 100-degree water, FYI. And this is the actual reaction that's taking place. You got some insight into this relationship that says the equilibrium constant for the acid and the equilibrium constant for the base are kind of working in tandem with each other to equal a constant at a certain temperature. And that says if you've got some conjugates, remember, like this acetate ion and the acetic acid, where they're the same chemical that differ by a hydrogen. And they're obviously weak, so one can accept and one can't. So weak conjugates have this relationship. And if Ka is really large, Kb would be really small. So if you've got the acid being fairly strong, like having a fairly high Ka, then this Kb will be really low. And you can, if you know one, you can figure out the other using the constant if it's at 25 degrees. You're getting a little insight into how we can turn every terrible number into a nice number. So the p equals negative log, and you can get different relationships, and you need to be mindful of some log rules every now and then, but you get used to it with a lot of practice. And so I just wanted to kind of give you a further insight. This is not so much as necessary introduction. This is kind of just a bit of more of an overview. We're covering a lot of weeks in one topic, so you'll go over these all again. But hypothetically, I've just started with this weak acid. This is ammonium, and the chlorine ion here is a spectator ion. I could substitute it out for a number of other things. It's not important, so it's just ammonium that I'm putting into the solution. Put in 40 mils, which isn't that significant, but the 0.4 moles per liter tells me a lot because I'm trying to deal with concentrations. So that's more important to me. 40 mils would come important if I was adding another substance, by the way. So I could ignore the 40 mils at this point. This is my concentration. And I wanted to kind of put it out to you that there's two reactions that are happening. There's ammonium that's splitting or ionizing or dissociating. It's transferring its hydrogen and acting as an acid and making the ammonia molecule. Because the Ka is very low, vast majority will still be in the ammonium form. But of course, you'll get some hydronium and you'll get equal amounts of ammonia. And people would go, well, ammonia is a base, so they should just cancel out each other and this should be pretty much neutral. But in reality, this ammonia is not a base itself. This ammonia has to further react. It has to, like another equilibrium, has to bump into water, make more of the ammonium, which is in itself kind of circular, and also make a small amount of hydroxide. So what I'm trying to get into your head is ammonium, given its Ka, is a weak acid relative to the stronger base. Ammonium will split apart a little bit, produce a little bit of ammonia. that small amount of ammonia will further react and produce hydroxide and also back for the ammonium ion. So it's a bit complicated, and I'm definitely not solving it right. I'm just trying to get you to appreciate two kind of simultaneous equilibriums. And there's other ways you can tackle this, like when we get down here. But this is just a way that I'm trying to get you to understand how two reactions can be happening simultaneously, or two equilibriums can be happening simultaneously. Now, you should be able to understand this Ka, this is products over reactants leaving out the water. And similarly to mod 5, this is kind of like an ice table done really lazily. This is minus x plus x plus x. And so ammonia's concentration at equilibrium will be 0.4 minus however many that dissociate or transfer. And then however many transfer over will make ammonia and hydronium ions. And x times x makes x squared. And then the equilibrium concentration of ammonium will just be its starting concentration minus x. And you can actually go solve that. It will turn into a quadratic because we do know Ka and we do know the initial concentration. But thankfully, we can do those small x approximations which popped up in mod 5. And we can avoid quadratic equations that you're not required to use in any HSC exam. So there's no point in us trying to do quadratics. And so if we approximate the 0.4 moles per liter minus x to be 0.4 moles per liter, then we can figure out the concentration of x, which is both ammonia and hydronium. And you chuck that in, which is a rearrangement of all this. You get the Ka minus the equilibrium concentration, which we've approximated to be the starting concentration, the initial concentration. And you get 1.5 times 10 to the negative 5 moles per liter. And you put that into pH, and that tells you it's a log of 4.82. Right? Sorry, not a log, a pH of 4.82. And you go, well, okay, we haven't really accounted for the ammonia then recontributing back some hydroxide, which would then neutralize some of the hydronium ion. So we go perform the exact kind of process with just a bit different numbers. So all the same thing. Kb, we've written ammonia acting as a base. Don't forget that. Do products over reactants. And then we rearrange to have hydroxide concentration because we're interested in that. And then we get Kb times the ammonia concentration. We've just figured that out. That's 1 times 5, 1.5 times 10 to the negative 5. And then the ammonium concentration, which we can kind of get a bit better now. We use the approximation up here, but we really don't need to use the approximation down here because we kind of solved for x. And I mean, we could really ignore that. 0.5 minus 0.4 minus that number is just basically going to be 0.4, by the way. So the approximation is going to be pretty sound. Anyway, you plug all these numbers in and you get a concentration for hydroxide being 6.75 times 10 to the negative 10. Now that's extremely low. And all I'm trying to get to you in your head is that is a really small contribution of base from your acid. Okay, so you put in quite a considerable concentration of ammonium, although most of it stayed in ammonium form. Some of it split over to the hydronium ion and the ammonia. And because ammonia, even though ammonia is a stronger base in that it ionizes a bit better, or that it dissociates a bit better, it's still a small amount splitting a little bit, so you're only going to get a little bit of hydroxide. And you go, okay, I know the processes weren't exact, and you pretty much get the same answer, maybe a tad higher, when you account for the reaction back. And so all I'm trying to get to go, well, yeah, the pH was slightly higher. That's because of what I was just saying about how you made a little bit of ammonia and therefore only a little bit of hydroxide back. But it is clear that you need to consider both reactions. And if we manipulate the first expression, the Ka1, and the reason why you want to manipulate the first one is because pH is only concerned with the hydronium ion, because it knows that if you only focus on one, then you can figure out the other based off the relationship. If this guy's really, really high, then pH will be low. If he's really high, then the hydroxide concentration will be really low. They're in tandem to each other. So knowing one basically indirectly tells you about the other. Anyway, the hydronium ion equals Ka times the ratio. And if you're wondering, this first one is just about conjugates. So if you've got the ratio of the conjugates, then you can determine the pH. So if you knew the concentration of ammonia and the concentration of ammonium and concentration of ammonia, you can actually work out the pH. If we turn this all into logs, all that is negative log of hydronium equals pH, negative log of Ka equals pKa, and negative log of of this one. You'll notice it flips and turns into a positive. There's two log laws going on there. It's not that important, but just take note. And you've got this equation. Now, this equation is technically outside the syllabus. It's called the Henderson-Hasselbalch equation. A lot of schools learn it because it's useful. And if you know the pH, it's going to be the negative log of the Ka, which you can look up, plus log over the ratio of these conjugates, okay, for these weak acid-base conjugates. Now, if they were equal in concentration, say 0.2 and 0.2, log of 1 is 0, and so it would just be the pKa. Okay? And if you go plug this all in, what is this trying to tell you? This is just saying that all that you need to know is the ratio of the conjugates and their Ka. So it's all about if he's high and he's low and how much you put into them. Now, the best thing about that is because it's all about the ratio of the conjugates and they're weak on both sides, you can pretty much just approximate their initial concentrations to be their starting concentrations to be their equilibrium concentrations. So I set up this scenario. I said, what if we into the same solution we had that 0.4 moles per liter, and we also had 0.3 moles per liter of ammonia. Now, I haven't done anything about the volume. You would need to technically worry about the volume. Like if I added 0.3 moles per liter into the initial solution because there was 40 mils of it, I won't exactly have that 0.4 or the 0.3. But I'm not fighting about that. I'm just saying that if I worked out their starting concentrations after they're mixed, all I'm concerned about is their ratio. So I can plug it into this equation and go ammonia has 0.3, ammonium has 0.4, and then I take the log of that ratio, the 3/4 ratio, and that tells me my pH went up a little bit. And what that tells you, so even though ammonia is smaller in concentration, and so you'd think it would be heavier towards the acid, what that's saying is ammonia is a stronger base, and so it's contributing more to your increased pH, right? And that's kind of inbuilt into the Ka. And so you got pH equals the pKa plus this ratio, and so my pH would actually be that. Now, where's this all going? You're going to work towards buffers. Buffers are weak acids and bases in an equilibrium. And we talked about right at the start, we talked about how every chemical has a specific pH range in which it stays in its certain structure. And outside that range, you can the solution may become too reactive for that structure. And so it's really important to keep a solution in a certain pH range. And in fact, the ocean and your body, both using this kind of chemistry, keep pH in a certain range. Now, your blood keeps it from memory about around 7.15 pH, and the ocean's around 8. And they use the same chemicals, which is the hydrogen carbonate ion in particular, but they use them to different ratios. Okay, and so you can calculate both of them if you look up their ratios. You can calculate both of them using what this equation, and for one answer you'll get 7.15, and for one answer you'll get 8.1, for instance. And it's interesting to note that like they have those systems in place to keep that kind of balance because the chemicals need to be in that balance. So there's you know a very complex system that your body goes under for your blood, and a very complex system that the ocean does on a super large scale to keep the pH in a certain range. Now, I'm not saying that it's doing that for the ocean, at least. It's not doing that with a conscious mind. It's just saying that there's this checks and balance system that allows pH to be kind of um, kept around the same range. And because it's kept around the same range, everything that lives within it can live within a consistent environment and not have issues. To give a bit more further to that, if I go back up to this one, what's happening in our oceans is called ocean acidification. We all know that CO2 gas is an issue in terms of climate change. One of those reasons is that if that concentration of CO2 gas goes up, then you get slightly more dissolved carbon dioxide. So, and then you get more carbonic acid. More carbonic acid means more acid. If you have more H3O plus, which I've just realized this one should say H3O plus, so I'll quickly change it. H3O plus. Then if there's more of this guy, then you'll get more of a reaction going back there, and you get the carbonate ion to go down. And it turns out this carbonate ion is the skeleton of so many crustaceans, even eggs. So calcium carbonate in particular, in different forms, is like eggs. It's like the backbone of like crustaceans, and we can monitor fossils and even living creatures. We can see their shells are thinning, and if you want to take it to one extreme, then you get like if the eggs get too thin, you can't obviously have any procreation going on. And if they become too skinny, they can't have their own structure, and maybe predators can get at them. So this can have kind of devastating effects. We can actually track our 6 major extinction periods, for which we're in one currently, to these to the fossils and how much they have, how thick their cells are. So if CO2 concentration is high in the air, then egg shells are thinner, and that correlates to our ice core measurements. And there's more to it. Like I've overlooked like this one. We all know CO2. Well, you might know that CO2 is in all your soft drinks, and you can bubble more into it when it's cold. So if it's increasing temperature, then you've got less CO2 aqueous, which means that that should be anti-ocean acidification. That should be like ocean alkalinity or basic. But because you're bumping more CO2 in the air, you can get more of the reaction happening forward, and yeah, it's more complicated. Like it's not just one thing happening; it's multiple things happening. Anyway, too complicated for the first one.